the source or the omega entry node identifies and stamps this packet with this flow ID, which is generated. And the source now floods the network with these path request messages in order to initiate the path discovery. And within this path requests, we use several QoS metrics. For example, the available link capacity, or delay, or jitter, or even packet loss. And these metrics should be handled differently, of course. And when this path request is transmitted from one hop to another, each intermediate hop has to update this path request message with respect to the quality of service, whether it can be ensured at this dedicated node, and has to rebroadcast this path request messages to the next ones in the network. Finally, when the path request reaches the destination node, the path reply is back propagated to the source node and activates the path by doing this. In case of a significant change of link metrics or a link failure or breakdown, a path error is generated. So let's have an example. Here, just think of, we want to set up a flow or two flows between node 7 and node 4 in this mesh network. And it doesn't matter which technologies are used, because we are looking on an InterMAC level, and this could be a PLC connection, whereas this could be a Wi-Fi connection, this could be wireless optics, and so on, whatever you want. And for simplicity, I just consider here one connection between each node for one technology, and not more technologies between two nodes. So, first of all, we want to set up a flow. This flow gets flow ID 5, and so 7 floods the network with path requests. To understand now the path selection tables, I will just explain. This is a time just for you for orientation in this example. This is the flow ID. This is the destination node. So it just could be the address. It's simplified. This is the next hop, which is not known at the moment. Here is the predecessor, which is 7. And this flag defines whether a route is set active or not. This means if there is a 1, the forwarding table within the data plane is triggered accordingly. So, there's the path request to flow ID 5. It reaches, after flooding the network, the destination node 4, and destination node 4 answers with a path reply along this path, which sets the forwarding tables accordingly here in this, on this path, and sets valid these entries. And here the entry is not valid, as you can see. So we want to set up another flow, which is flow ID 9. And of course, again, the network is flooded. And maybe for this, another path could be used. This is the example, for example, if we want to set up two parallel multimedia streams, and the one stream does not fit into the path which has been selected before, for example. So, path replies are back propagated to the source, and after a certain time, the entries in the path selection table, which are not set valid, expire and they are deleted. And finally, we end up in two paths which are set up for flow IDs 5 and 9. So, this is the basic procedure. Now imagine that a link break happens between 8 and 4. Now, of course, 8 detects that this link is broken and sends out a path error to its predecessor, and in this case it is already the source. So, path error for flow ID 5. Now, 7 again has to find a new path to the destination node, and for this it floods the network with path requests again. Of course, 4 answers again with a path reply. And we found one alternative path for flow ID5. So both flows are going over this path. And again, after a certain time, this entry is deleted. So this is actually how the path selection works. The path selection is supported by the monitoring engine. As I already said, the monitoring engine provides the interaction with the technologies by the InterMAC adapters. And thus it extracts the technology-dependent information from the InterMAC adapters. So it continuously receives link statistics from the data plane, because there's the actual interface. And the monitoring engine calculates link metrics, for example, the hop count, or maybe something like a soft hop count. You can weight certain hop counts with reliability, for example, or some other metrics if you want to. And there are metrics like delay or jitter, packet loss rate, and the local interface load is also very reasonable metric. Another task of the monitoring engine is to trigger the link events, which are a link is going down, link degradation, or another link appears. And this is provided as input to the path selection engine. So there's a system similar to IEEE 802.21, which is this event mechanism. We have events and subscribers of these events, and they are raised within the device. So now we'll address the specific problem for InterMAC adapters. If there are no InterMAC adapters which are perfectly adapted to the InterMAC, which has been developed in Omega, we had to find a way to interoperate with commercially available stuff. And therefore we tried something very, let's say, which can be scaled, which is scalable for many technologies, and which happens actually in the data plane. Here you see 3 interfaces: interface 0, interface 1, and interface 2. And this may be technology-dependent interface. There may be some network adapters you can get from the shops, for example. It's 11N, or maybe a PLC adapter, or 60 GHz radios. You have seen it in the showroom, actually. The monitoring engine in the control plane subscribes to a data plane monitoring service. That means it periodically receives the interface link statistics. And by subscribing to this service, of course, you can define how often you want to get these metrics and how often they should be refreshed, of course. Each interface is associated with a probe frame frequency and a certain link down after. So when you want to raise an event that the link goes down, this differs for certain technologies. In Ethernet, you can immediately say, okay, this link is not working anymore. But in wireless, for example, it is much more difficult. And if you even consider 60 GHz line of sight communication, where the line of sight path is very, very important for the communication link, just if a person walks through the line of sight path, the connection can be lost. But immediately after it is gone, the connection is re-established again. So certainly this link down afters have to be different for the technologies. Now, when there's no user traffic, we are using probe frames at the interface. And these probe frames are injected into the network, or not in the network, sorry, onto the link by the data plane. Now, in case a probe frame cannot be transmitted and the answer, the acknowledgement is not received, a link down event can be raised. So we know for future path selection procedures, this link is not available anymore. So the probe frames allow for measurement of interface capabilities. You can do stress tests, for example. You can stress an interface and see how much traffic goes through there, through this interface. So the probe frames are somehow the heartbeat of these living interfaces. And when they are dead, they are not existing anymore. This is an analogy. Finally, they are configured separately for each interface, as I already have mentioned. Now, consider ongoing user data traffic. Each interface may be delivering a certain traffic at a certain bit rate, and a table which is located in data plane counts the number of bytes which have been transmitted over this interface. And by means of this, for example for power line communication, or also for internet, it is possible to estimate the link load and the remaining capacity at this interface, at this node. And of course you can calculate link metrics if you have some sophisticated algorithms which need these basic information. But, as I already said, InterMAC adapters are needed when you want to use a technology at its best. And therefore InterMAC adapters should be integrated into the system to make available technology-dependent information to the InterMAC. These are, for example, MAC MIB elements, as they are described, for example, in an MIB of an 11N system. The InterMAC adapters enable technology-dependent functionalities, and it allows also to provide an added value to existing network technologies, as I will show you now. For example, we have developed a wireless LAN InterMAC adapter, which is able to periodically report the current channel load. So this is the time the air channel is occupied. And on demand, it sends link capacity estimates to a specific station. So we have developed an algorithm which allows to take into account a certain modulation and coding scheme, which actually represents the data rate you are going to use. And because of the history and the information from the rate control in the network device, combined with the channel busy fraction, you are able to estimate the capacity, but only to estimate. You cannot, for a wireless device, you cannot say what will be the available capacity. You can just estimate it. But this is much more than we know in today's devices, the devices of today. And for example, we demonstrated a handover down in the showroom, and we have a handover which is based on the received signal strength indicator, which is provided by our network interface card, which was an Everos card. And this addresses a certain omega objective, which was that the closer, the higher the data rate. This is very important because if you are connected to a certain access point on one place, and as closer the distance is to this access point, the higher the data rate will be, because the signal-to-noise ratio is better. When you move away from this station, and maybe another access point is located next to you, maybe in another room or so on, you can move to this, and based on the InterMAC adapter, the information from the InterMAC adapter, it is possible to recognize that there is an access point with a higher received signal strength indicator, and so you perform intra-technology handover. We can just see this in this small scenario. We have traffic from N4 to N3, which uses the wireless LAN link here and an Ethernet link here. And this is shall demonstrate somehow the wireless LAN at node N1 and 2, and this the wireless LAN network at N1. And now node 4 is moving. And of course, this link is not used in the beginning, and as it moves towards this direction here, the RSSI will increase for this node, for N2, as you can see it in the diagram here. And accordingly, handover is performed. And you have seen this actually in the showrooms. Such link events, so switching from one access point to another, are reported to the InterMAC, and they facilitate the path reconfiguration.